Alright, so we're going to look at some other aspects of probability and basically counting mechanisms that we can use to help us with probabilities. And so the first thing we're going to do is we're going to look at permutations. And so, whoops, let me redo that. That is not what I wanted here. That was an old set of notes. There we go. So, imagine we have three colored objects, RBG, red, blue, green. And we want to know how many different ways we can arrange these. And so one permutation is red first, then blue, then green. And so these are going to be called permutations. And it's the how many arrangements of n objects you can get. And so it's an ordered arrangement of n objects. So order matters. So if I have three objects and I need to know every possible order I can get from them, well, let's look at this. I can start with red and then have blue next, or have green. I can start with red, but I've already had blue next, so I should choose green next, and then blue. I kind of think of them, if you think of them as being in some sort of urn, and you reach in to grab one. Alright, this says we grab the red one first. Well, if I don't replace it back in and I go to grab the next one, I have the choice of getting blue or green. If I grab the green one, the only one left is blue. So notice the first time I go to grab in, there's three items. And once I pull one out, that leaves two items. And I pull another one of those out, and that leaves me with one choice left. And so permutations and this orders kind of build up from that. So let's say I pull a blue one first. Oops, nope, I hit green. See, that's what a little bit of randomness does for you. So next I can get blue or red, because that's all that's left in the urn. On the other option I have for green is, well, I've already pulled blue, so let's say red. So for pulling red, there are two possible patterns I can do first. Pulling green first, there's two possible patterns. And I would surmise that pulling blue first, now I reach in and I grab red, and that leaves only green left in the urn. Or I could have grabbed blue, and then got green, then red. And this has all the combinations, or permutations I should say, that I could possibly get out of this. And so there are 1, 2, 3, 4, 5, 6 permutations. And what we say is, if we look at it, when I first go to pull, there are 3 options. When I next go to pull, there are 2 options. When I last go to pull, there's 1 option. Well, we said that the number of total possible options is a multiplication of all the choices, just like we did with the menu items. But in this case, each time I pull one out, I have less options to go. And this is a very special series of numbers. We write it as 3 factorial. And 3 factorial means 3 times 2 times 1. So 4 factorial would be 4 times 2, or times 3, times 2, times 1. And so it's whatever this number is multiplied by every integer that comes before it. Now to make this work, we have to kind of look at the base of it. So if I have 1 factorial, I have one object in my urn, how many ways do I have for it to come out? Well, I have one possible way. If I have 0 things, how many ways do I have it to come out? 0 factorial. And if we think for a moment, well, nothing comes out, but that's a way, and it's only one way. And so 0 factorial is also equal to 1. And so we define our factorial, where 0 factorial equals 1, 1 factorial equals 1, 2 factorial equals 2 times 1, 3 factorial equals 3 times 2 times 1, 4 factorial equals 4 times 3 times 2 times 1. And so any number n factorial, is going to equal n minus n times n minus 1 times n minus 2 times, I'll put some dots here, 3, 2, 1. Alright, and so you take whatever the nth number is and you slowly count your way back down to 1, and that gives you what a factorial is. And so permutations determine how many possible outcomes there can be. So, for example, in the book, if you look at a Sudoku, which is a 9x9 grid, divided into 3x3 grids. Each of these has 3 in them. Bunch of little tic-tac-toe grids to say that these are divided 3 by 3 by 3. Right? And so each one of these is filled with the numbers 1 through 9. And so the first row has 9 entries. But once you put one number in, it can't repeat. And so the number of ways to fill in one row in Sudoku is 9 factorial. Or 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is equal to 362,880 ways. Now, what we're working towards here is the probability based off of the number of choices we have. And we want to find a way to count the number of choices that manifest themselves. And so factorials is one way of doing it. The other thing we can do is we can do the permutation of n objects. Taken at r times. And each of these objects are distinct. And so what we're going to say is, let's say that we have 10 possible digits. Right? We'll use numbers. But we're only going to draw 4 of them to make a pin. And that's what we mean taken r different ways. So if I have 10 different things, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but I can only use 4 of them without repeating. Remember, we had this problem earlier, and we kind of figured it out loosey-goosey. But what we can say is, we can write this as 10 permutations 4. And what it's going to be is, it's going to be 10 factorial over 10 minus 4 factorial, which is equal to 10 factorial divided by 6 factorial. Now here's the real trick to this. Everyone wants to run to their calculators because factorials get so big so quickly, right? We did 9 and that was 362,880. So 10 would be 3,600,000 628,800. Right? You put a 0 on the end of what we did before. And then divide that by 6 factorial, we have to calculate what 6 factorial is. But numbers and factors do nice things, so if I were to write this out, and write the 6 factorial out, well, notice I have these factors that are the same in the numerator and denominator that cancel out. They turn to 1, right? 6 over 6 is 1, 5 over 5 is 1. And so they don't change the value if they're in pairs like this. And so any smaller factorial under a larger factorial is going to chomp down for the numbers after it. And this is a much easier calculation because this is 5,040 ways. And so if I have a 4-digit PIN and I cannot repeat numbers, well, we did it before by saying, well, we have 10, and then we said, well, we have one less number, we have 9, well, we have one less number, we have 8, we have one less number, we have 7. Well, that's what's here. And so we actually have a formula that we can use for this, finding these permutations. And so the formula is how many things I have total and how many of them I'm picking. And so we get n factorial over n minus r factorial. And this is a common way of choosing arrangements of items. So another example is there are 33 race cars in the Indy 500. And there are 3 positions, first, second, and third. So how many possible first, second, and thirds are there, right? You know, Bob, Andy, Gene, Kate, Steve, Stefan, so on, right? You have 33 cars. But only 3 of them can be first, second, third. And, you know, so you could have Andy first, Gene second, Kate third, or Kate first, Andy, Gene, right? These are all the different permutations we can see out of these 33 racers. And so the number of ways is going to be 33 choosing 3, or 33 factorial divided by 33 minus 3 factorial. And again, this is 33 times 32 times 31 times 30 times 29 all the way down to 1 over, well, 33 minus 3 is 30, so that's 30 times 29 all the way down to 1. These will mitigate each other, and leaving me with 33 times 32 times 31, or 32,736. And so one of the key takeaways from this is how quickly choice leads to many different patterns that we can look at. And part of what we're going to look at here are these different permutations of objects, distinct objects in the order we have it. So we have when we want the number of permutations from every possible object in a count, it's n factorial. When we want the number of permutations when we choose a distinct amount from that, right? And I always kind of say this, n pick r, right? I have 33 things, I pick 3 of them. Well, how many different patterns of those 3 things we can get? And that's n factorial over n minus r factorial. And so those are permutations.